Hi, Tomas.
Oh, hello. How are you?
Great. So, are you ready?
I'm ready. How do I share the slide here?
You should have some button on the left, green button, or on the right, like a menu, three dots.
I see screen share.
Yes.
Okay. Share. And now, do you see the slide?
Yes, we can see it. So, wait for a minute. I will ask people to come from coffee break. So, just wait for the few seconds.
Okay. Fine.
So, good evening, everybody. It's my great pleasure to present our next speaker, and we will have the final talk of our school. So it's actually not pleasure that it's final talk of our school, but it's great pleasure that we have such great speaker for the last talk. And so I think that it will be a good finalizing point of our lecture program. So let's welcome Tomas Mikolov from Facebook AI Research on our school. And so, Tomas, please proceed with your talk.
Okay, I can start. Thank you for the introduction. So we'll be talking today about neural networks and how they are used in various NLP applications. It's not a complicated talk. My main point will be that it's very useful actually to consider using neural networks for tons of tasks, but we can also do very well with very simple techniques, and I will describe them. Stuff like, for example, recurrent networks and word-to-vec, like all these models can be seen as something actually quite simple, and often we don't need to add any unnecessary complexity to get very good results. So that's already like what I will try to explain in the whole talk. So to start, I think I don't have to convince people that it's clear that text processing is actually very important for many important big companies nowadays, like Google, Facebook, and all these search engines. And messaging platforms are actually dealing with tons of text data, for example, user queries or user messages, and you have to do something with them to make the users happy. For example, you want to give them the most relevant search results, or you want to filter out the spam. There's like tons of these tasks that we would want to do very well on. And we can use for many of these tasks actually neural networks. The whole framework of neural networks is very simple. We can use them for classification or for modeling sequences, and that's the main points that I will be talking about today. So for example, for the unsupervised learning of the word representations, we can use word2vec, and it's great in cases where we have tons of data and no supervision signal, so we don't actually really know what we want to do. We just want to model the text data somehow and get some insight into what is in it. And when we actually do have the supervised signal, for example, we know that some message is a spam or it is not a spam. That can be seen as the supervision signal. For that, we can use tools like FastText that I will talk about a bit later. It's a library for both learning of the word representations and for doing the classification. And for modeling sequences, we can use recurrent networks. These are very popular nowadays. I think there's often much more complexity than is necessary to make these models work well, and I will explain this a bit later. Of course, there are these interesting research questions. What do we want to do next? So there are like these long-term goals that we have like for 10 years into the future, what we would like to discover, that we would like to develop some communication agents that you can teach using just natural communication. For that, we are thinking about building virtual environments. We actually did make some that we did share last year. and I will describe basically this at the last part of the talk. So for the basic machine learning applies to natural language processing that I think people already know about. So I will just briefly mention them. There are n-grams and back-of-words representations and word classes. I think that's actually very good to start with. And before people jump into the state-of-the-art deep neural networks in NLP, they should really know these concepts well, because it's actually very useful, at least to have a baseline, and sometimes they are actually enough. And for classification, logistic regression should be well understood before people try to use neural networks as well, because actually it's pretty much the same concept, just the neural networks are adding the hidden layers. And so in some cases, we can actually improve over these basic representations and classifiers by using neural networks, but not in all of the cases. So as I said, it's very good if people start with these and have a good understanding what is doable with simple counting before they jump into the deep learning. For a quick introduction to neural networks, I think that many people already know this. I will go a little bit quickly over the slides, but I think it can be a good refresher in any case. So we have like these basic components like neurons, layers, synapses, activation function, and objective function. And I will basically describe these terms a little bit quickly. The main motivation for using neural networks in natural language processing is to simply come up with more precise techniques and solutions than what I mentioned before. So better than n-grams when modeling sequences, and better than logistic regression when doing text classification. That's the whole motivation, to simply improve the existing tasks. Of course, the high-level motivation would be also to come up with techniques that can do something that is not really doable with the traditional NLP techniques, but we don't really have any such result yet in the community. There's basically nothing that we can do well with neural networks that we cannot do with something that's based, for example, on counting. There is this performance difference, that's true, but there's no like miracle solution. But it's always good to be the best if you want to have the best search engine or best results in a competition. So it's definitely great to work on neural networks, even if they are not as super novel as the name might suggest to some. It's definitely not a solution to AI yet. So this is the model of neuron. Like it's from the 60s when people did come up with this perceptron model that is approximating the biological neurons, but it's actually like very, very crude approximation. So it's better to see artificial neural networks as mathematical models, not really a simulation of the brain, as sometimes is mistakenly claimed. So there are like these input signals coming to this unit that we call neuron, after where these signals are summed together with weight that are given for each synapse. And then an activation function is applied, and the resulting number is basically the output of the neuron. So the most simple neuron can be seen as, for example, this. We have 3 weights and 3 inputs. We multiply the weights by the incoming signal, apply the activation function, and produce the output, which can be seen as some real value signal. So it's actually very simple. Neural networks are about like placing these neurons, artificial neurons, in some architectures. So we connect the input features with the output features by going through several layers of these neurons. So as I said, it's definitely not the same as biological neurons. There are like so many differences that I will not even talk about them. But it's interesting to also see the brain as some information processing system. And for that reason, we can say that there is some slight similarity between artificial neural networks and the biological neurons, because both systems are sending information and processing them through some computational units. The learning in the brain definitely doesn't work the same way as it is typical for these neural nets. We don't do SGD in the brain. Also, some people would like to believe that it's true, but the brain's learn quite differently, and actually nobody really understands how does it exactly work in the brain. So it's better if we leave the analogy with the real neural networks and just focus on the mathematical side. In that case, we can see artificial neural networks as basically some nonlinear projections of the input data that we can stack on top of each other, and that's pretty much all. This is how it can look like in a graphical representation. You have neurons at the input, 3 neurons at the output, and some hidden neurons. And if we connect the neurons this way, we can say that there are 3 layers. Sometimes people would say that there are 2 because some do not count the input layer as a layer, but I do. So let's say that there are 3 layers with this connectivity. So there's just one hidden layer. And we can do like whatever tasks we like if we train the network using, for example, the backpropagation algorithm. That's with stochastic gradient descent. That's the most popular choice nowadays, and in my opinion, it's pretty much the best one to at least start with. And I don't really think that it's possible to improve over SGD and backpropagation by a large margin. Usually it's the best thing. So the whole idea of backpropagation is or stochastic gradient descent is very simple. For each input feature vector that we present at the input layer, we typically know what is the output vector that the network should have been producing at the output layer. We can also compute what would it produce with the current set of weights that it has. And then we know how big mistake did the network do, like how big is the difference between what the network did compute and what should have been at the output layer. And we just change the weights slightly so that next time the network would see the same input feature vector, it would produce such output vector that would be closer to the desired output. So it's like very simple to understand, and that's the whole logic of SGD. And then the backpropagation algorithm is just about how to compute these changes of the weights in the weights that are not directly connected to the output layer. So there's some math that I will not be describing. People do not even need to see these equations anymore because there's tons of toolkits that do this in the background. But this is the main principle. We can also think of a simplified graphical representation that I have here at the bottom right, so that we would not need to draw all the neurons individually, but we can just say that there are these boxes that contain n neurons, and there are these feed-forward signals that are coming from left to right. That's the black arrows, and then the training goes just the opposite way, going from the output layer, propagating the gradients and updating the weights at the same time. Training usually means that we present the network all the training examples from the training set one by one, and we update the weights frequently. After each training example, we can update the weights or we can batch them, but that's already like the implementation details. Typically, the training doesn't do quite a lot of things that programmers have to choose manually, which is like what is the type of the activation function, what is the nonlinearity there, and what is the architecture, like how many layers there will be, and their sizes. That actually can be also learned using, for example, evolutionary strategies. But typically people do not do this, maybe more in the future. Also the starting learning rate, how quickly does the learning rate decrease? The learning rate means how quickly we will be changing the weights. If the learning rate is small, then we always update the weights only slightly. So if you have a very small learning rate, then the network will forget slowly the information that it learned, but it will be also inflexible, and it will learn very slowly the new information. If we set the learning rate to high value, then the network learns quickly the recent examples, but it will be forgetting also quickly what it learned before. So there is this trade-off of choosing the right learning rate, which actually is something that I would say it's like very important for like achieving good performance. That's something that people should definitely tune together with the size of the hidden layer. So And then, of course, the feature engineering, like what features do we present at the input, how do we normalize them, and so on, and how do we regularize the model. We can use model ensembles or dropouts. These two things are pretty much the same stuff. So that's all these choices have to be done by the engineer or researcher who is using the neural network. So it can be a little bit overwhelming in the beginning, but nowadays there's tons of tutorials how to train a good network, for example, for ImageNet classification or bench bank language modeling and so on. So it's actually not nearly as painful as it used to be 10 years ago to start working with these models. Deep learning is something that is getting a lot of attention nowadays. I think that it changed the meaning from what it used to mean originally. So now I think people call deep learning pretty much everything in machine learning that can be seen as some form of neural network. So I think some people count even logistic regression as deep learning, which I don't. Originally, the term that supposed to mean a model that does n nonlinear computational steps before it produces output, where n was supposed to be bigger than 2 or 3. So you can see it as a neural network that has more than 3 hidden layers would be considered deep, and if it has less than 3 layers, then it would be considered shallow. That was like the distinction from, I think, like 10 years ago when people started using this term. And nowadays it's more difficult to say what it is deep learning and what is already something else. Original motivation for deep learning was not just to have more layers, but to explain it simply because neural networks can be seen on the mathematical side as also weighted Boolean expressions. Because of the nonlinearity. It can basically compute things like feature number 1 and feature number 2 means that some neuron gets activated, or it can implement the Boolean function OR. And because we are working with the real numbers, then everything can be seen as weighted. So if we see neural network as some Boolean circuit, then the depth basically means that we can express some functions more efficiently using deeper network than a very wide shallow network, which is like 100 years old results from the community that did work on the Boolean circuits. I think it's like in every computer, when you want to, for example, multiply numbers, there's like this low-level hardware that actually is using several computational steps. So exactly the same logic is in the neural network community, and the deep learning aims to build models that are using several computational steps to more efficiently represent the functions that we are trying to learn. And if you can represent them more efficiently, that means that you need less parameters to learn, which also means that you will need less training examples to start generalizing well. So that's the whole motivation. And of course, there were like people like Marvin Minsky and Seymour Papert who were already advocating for studying more richer computational models than perceptrons, already in their book, like from the last century. It's almost 50 years ago that they did publish it, where they did show a number of examples that are either very hard to be learned with perceptrons, or they did even prove that for some of them, the shallow networks will have to be unnecessarily large, for example, for the parity function, in which case it would basically have to see all the possible combination of input bits to be able to produce correctly the output. The motivation for deep learning, this is a graphical representation. Simply with 3 hidden layers, it would look like this. So there's nothing complicated. Everything works the same as before. Of course, the gradients, and they are propagated through the structure. It's a little bit harder than in the more shallow network. So there's a lot of like these discussions, what is the best activation function to use, and where you can have some skip connections so that you would go, for example, from a hidden layer number 1 directly to the output layer, and so on. You can do all these things, but the basic idea is just to have architecture of this type, and it already somewhat works on some problems. But of course, this is the deep neural net. What people usually use nowadays is some network that is using the our understanding of the input signal that is encoded at the input layer, because there's often some topology that we can exploit and recode in the network. For example, if we are dealing with some sequential data, then people would naturally choose nowadays recurrent networks that are having the depth through the recurrence. I will describe that later. And for some types of signals like images, where you have the 2D structure of the input signal, people use convolution networks that are sharing the parameters across different positions of the input signal. So I don't think that the deep networks are that much used, like the purely deep networks are that much used nowadays. Mostly people use either recurrent or convolution networks. So, certainly, deep learning is still an open research problem because there's like many things that we still don't really understand well, and we can't really learn all the complicated patterns that these networks can express. So that's also interesting. So the SGD, for example, will get stuck in local minima when we try to train them on some more complicated tasks. That's what I will be showing at the end of the talk. There's also a lot of hype when people claim that these models can learn something which they in principle actually cannot learn, which is kind of funny. You may be wondering why I'm saying that, because it doesn't seem to make that much sense, but there's this old argument of universal approximator, that if you have one hidden layer, that's enough to learn anything. But that's somewhat misleading. That just means that if you have one hidden layer that is sufficiently large, then you can actually memorize everything. That means that if you see in your training data everything that you will see in the test data, that with 0 hidden layers, you can't actually memorize it, because there are some examples like XOR function that you can't memorize. It's like super simple. But with one hidden layer, you already can memorize everything. But that doesn't mean that you can actually learn it. So I think that's something that people should realize, that if their test data is exactly the same distribution as the training data, and even the examples are pretty much the same, then the network might not be generalizing and solving the problem, but it may be just simply memorizing it. So that's one of the complexities of understanding what are the limitations of these models. And of course, there's many applications of deep models that have multiple hidden layers, where they are evaluated on problems like, say, text classification, where they actually achieve nothing else than what a shallow model would learn. In which case, I would say that's like the bad type of hype, when people just jump on the most complicated model, and they are making big claims and conclusions more for the PR reasons than for anything else. So now for something more concrete, some application of a neural network for learning features from text can be by using a feed-forward model. It's actually very simple, and that's what I will describe in this part of the talk. It's basically the word-to-vec model, and how do we get to it? We can start with a very simple neural net that can be seen as a bigram language model. Imagine that you have a stream of words, and you are trying to build a neural network where, given the current word, you are trying to predict the next word, the future word in the sequence by going through one hidden layer. So it's very simple. There are just these two weight matrices between the current word and the hidden layer, and between the hidden layer and the next word. And the next word is encoded as one of n, the same for the current word. If you will train this bigram language model, then it will actually learn to cluster the input words that have similar meaning or appear in similar contexts together. So, for example, France and Italy will have a similar feature representation, where the feature representation basically comes from this matrix between the current word and the hidden layer. And that's kind of interesting observation. We can get, of course, a better model than this one. So people did work on these word vectors in the neural network community, like since maybe 2008, when Ron Colbert did publish his influential paper on this topic, where he was using some convolutional networks for training these word vectors. But actually, people did use feedforward network even before him for learning these vector representations. And they have like a very interesting properties that are similar to the word classes, but are actually better in some ways. These feature vectors, these vector representation of words, vector representation of words can be actually very useful for transfer learning applications, where we actually learn from some task where we have tons of data, these feature representations, and use them for another task where you have less data. That's the most typical case. For example, imagine that you want to do classification. If you have just few hundreds of labeled examples, if you will train your classifier right away, then it's not going to generalize very well. But if you will use the pre-trained features, then your classifier can learn much more efficiently from these feature vectors, because already like words are clustered somewhat together and so on. So it's much easier to generalize. As I said, there were like many of these neural architectures that are proposed for learning the word vectors, and many of them actually were adding the depth and like more hidden layers, which actually some people like me did believe was unnecessary. So hard actually to argue with is better, but there was this interesting paper that we did write at Microsoft Research that actually did allow us to compare different architectures for learning the word vectors and see which one encodes more of the information in the language. So the observation was very simple and quite insightful for like the structure of the language. It was basically that these vector representations do not encode just like clusters of words, but more like directions or subspaces of the language space. So, for example, there is this well-known example that if you take the feature vectors for words king, man, and woman, and do this calculation, king minus man plus woman with vectors, and then do the nearest neighbor search, then you will get queen as the result, which is like exactly what we would like to see. And there's many of the other similar regularities in the feature space. If we learn very good vectors, then we can actually get extremely high accuracy for these calculations. It's almost magical. We were also surprised how far did it go with the accuracy of these models. So the data that we later used for comparison of these different ways how to train the word representations, this is the one that we developed at Google in 2012 and published in 2013. It has about 20,000 analogy questions of this type. Some of them are like more on the semantic side and are not actually all that trivial. You have to, for example, be able to say what is the currency of Iran based on an example of what is the currency in Angola. That's actually quite difficult even for people. And then there are like these more like syntactic regularities that are actually quite easy for people. But then if you consider that the models do not see the structure of the words, but they just see the one-up encodes, then actually it's quite interesting that you can do well on these examples as well. These word-based examples, we did also develop a phrase-based data set, so it's not just about single words, but about like these named entities. You have to be able to identify them in the training set and then compute like all these interesting things. And it actually works quite well. We can get like very high accuracies on these data sets with good models. So now back to the neural network. So people were often using this architecture that was proposed by Yoshua Bengio in around 2003 that did use engram encoding, or it used this feedforward architecture for encoding several words at the input layer, usually like 3, 4, 5, 6, or a few of them. Then a projection layer where the matrices U are actually shared across positions. The projection layer was linear, then there was nonlinear hidden layer, and then there was the output layer that they try to predict what is the next word. So that's the feedforward neural language model. And people that train these models often for the task of learning just the matrix U, just the word vectors. It's also interesting to notice that if you optimize this model well, using some tricks how to deal with the big softmax at the output layer, then the majority of the computation is actually between the projection layer and the hidden layer. So that's the matrix V. So it seemed very inefficient that people were training these models for like weeks and even months in some cases. And at the end of the training, they did basically throw away most of these parameters from the model that actually did take all that time, and then they were just using the matrix U. So that seemed very wasteful. And people like me did have the idea to actually do it in a simpler way. And that's if we would actually look at the original bigram language model, then actually it doesn't have this problem. It doesn't have that computation between projection layer and the hidden layer, because basically there's just one hidden layer and all the computations can be actually super fast in this model. It doesn't produce actually as good word vectors as the previous model. It's not as good as the feedforward language model for learning the word representations. For example, if you would evaluate it on the word analogies, it would be pretty bad. But then if you look back at the feedforward model, it's actually just adding context when we are trying to do the prediction, and it's also doing this nonlinear step, so it allows to learn some sort of engrams from the inputs. So that's all fine, but if we care just about the word vectors, maybe we do not really need a real language model. Maybe we don't need the ability to learn engrams. Maybe just the individual words and enough of context would be. And so that was the motivation for this architecture. That actually is not a language model. It's a word vector learning model. So we care just about the word representations. We don't really care about the task of doing the prediction, although this is what we are optimizing. But we really want to get good features. And that's all. So we just add more of the context by actually having more words encoded at the input, both from the future and from the past when we are trying to predict the current word. And we are just summing their their vector representations in the projection layer. There's no hidden layer, so we directly do a softmax at the output layer, which then is optimized. And this architecture is actually like orders of magnitude faster than the Ngram neural net language model from Yoshi Bengio. Like for big data sets, it would be probably 10,000 times faster to train. So it's a huge speed up, and we can train models on like completely different scale with architecture. Then a mirror architecture to the continuous backwards architecture is the skipgram architecture. That is maybe even simpler to understand, where we simply take the current word in a sentence and we try to predict one by one the nearby words, and we propagate the gradients through these weight matrices, update them, so update the weight matrices. So that's both architectures are very simple and can be trained on billions of words in like a few minutes. Of course, we still stick with the basic SGD and backpropagation. People actually tried to use even different learning algorithms for these architectures, but I do not know about anything that would be able to beat the SGD. Then, as I said, there needs to be some solution for the large softmax layer at the output, which encodes the probability distribution over all possible next words, which you can imagine can be easily hundreds of thousands or even millions of outputs. So in practice, we do not want to evaluate this huge number of possible future words given the history. We just want to evaluate some very small subset, and for that there are these two techniques, the hierarchical softmax that has the idea of basically evaluating just some clusters over clusters of words. So you are trying to just compute some very small subset of the outputs from all of them. And the negative sampling is completely giving up on the idea that there will be probability distribution computed at the output layer, and it just assumes that the outputs are one against all small classifiers that are independent on each other, and you evaluate for every training step just the positive example, that is the word that does really occur in the context as a positive example, and few randomly selected negative examples. So it's actually even much simpler than the hierarchical softmax. So it has the problem, it doesn't actually give you good good probabilistic model. It doesn't compute, it doesn't converge to good probabilities in the language modeling sense. But if you care just about the word vectors, then it's actually completely fine. And it's the simplest algorithm to implement. The other trick that that we introduced in the word2vec was to subsample the frequent words. It's also very simple to explain. We are dropping with some probability the most frequent words so that we both reduce the amount of training data and the amount of gradients that is coming from these super frequent words. Interestingly, it improves significantly the quality of the model. That's one of the tricks that also wasn't known before word2vec, and now people use it a lot because it improves the results and the speed at the same time, the training speed. This is the comparison that I was talking about. So I said there was a lot of these word vectors that were published together with usually some analysis on some supervised tasks where people did take these pre-trained feature vectors and they did use them for supervised tasks like name entity recognition. And they did observe that if you do not use the pre-trained vectors, you have, for example, accuracy 78%, and then with the word vectors you get to 78.5%, and then people try to make conclusions about the different techniques, which was very difficult because you can imagine that that if you are just jumping around like by plus minus 0.5%, you will not really see much difference between different techniques, how they are actually good in general for learning the word vectors. On the other hand, the analogy data sets that I was showing are much more sensitive because they are not used together with anything else. They just need to have very good word vectors, and the quality of the algorithm is actually much more visible. So if you, for example, take some existing code for learning the word vectors and you will make some small mistake in how the gradient is computed, you can actually see it very easily on these analogy data sets. The accuracies will just drop down. So the models that were quite popular in the neural network community back in the day, like in 2012 and so on, are like these several models. One was from Ron and Colbert, who trained his model on, I think, Wikipedia for 2 months. It was like surprisingly long. Like he trained, because he was training basically the model with the complexity of the Yoshia Bengio's model. So it's not that surprising that it took so long, but anyways, it was one of the most frequently used models back then. And there was Joseph Durian's implementation that it also trained for weeks. And actually his vectors were pretty bad. And then there was Andrew Mnich, who did use the block bilinear language model. Also the trained for like quite a few days. And then I had the recurrent network language model vectors that were also public on my website, that was trained also like on hundreds of millions of words in weeks. And it was a way larger model than the others. So for example, in perplexity, the recurrent network would be beating all the other models by a lot. And then there was a model from Stanford that was trained on almost 1 billion words, but with just 50-dimensional vectors. And the accuracies on the analogy data sets were like quite revealing that you should be using probably as much data as you can and as large dimensionality as you can for these models. Later we did find that actually like around 300 is enough for like the word2vec type algorithms. And then there are these two last lines, which are the architectures that I just described, the Scapegram and the CBAR architectures, and they basically go to hours or minutes while they reach like a completely different level of accuracy. So it's way better vectors for encoding both the semantic and the syntactic information. I think that did convince a lot of people to give up on the idea that word vectors are like any sort of like success of deep learning, which used to be the main message, for example, from people like Yoshia Bengio in 2012. And I think this convinced him that we can actually train even much simpler models much better and much faster. So the next steps were obviously like scaling everything up to train the models on more and more data. We did publish the code actually this link probably doesn't work anymore. I think it was shut down somewhat recently, but there's there are like other copies of Word2Vec. For example, I have a copy at GitHub, but there's also a follow-up project that we are developing here at Facebook that's called FastText. So if people want to use Word2Vec, it's implemented in FastText, so they can look at that. And then there are like these examples of how it looks like. It looks like if you look at the nearest neighbors, like the difference between the models is of course huge. Like if you look at some less frequent words, like say graffiti, you can see that they are like pretty big mistakes for like all the models except the skip ground that was trained on the largest data set. Then there are like these other funny analogies that you can find in the papers that we published, which is more like for fun than anything else. That you can, for example, take sushi minus Japan plus Germany, and you end up with bratwurst. So it's kind of fun to play with these models around, and I think it's also actually useful for people who are doing data science and data analysis. If you are working in a company where you have like tons of data coming from the users and you want to figure out what are the recent trends, then you don't really need to do these calculations, but you can definitely look at how like the word vector space is evolving in time. This like visualization of the word vector, we did show that there's actually like clustering happening at several levels. It's not just that similar words would get clustered together, but even like there's this linear relationship between the countries and capital cities. So it's like several attempts to get better than Word2Vec. Some were more successful, some were less. There was like one famous example from Stanford NLP group that tried to implement Word2Vec by changing the algorithm, and instead of seeing it as a neural network, they tried to first count the word concurrencies in some small windows, exactly the same as Word2Vec does. But they don't compute the damage, the reduction at the same time. They just do it in the second step. And they did claim that it has superior performance to Word2Vec. It's from their paper that they actually, from our first paper, pretty much the worst results they did find, and they did claim that their glove is much better. If you look at the table, it seems quite convincing. You basically get with much lower dimensionality vectors, 75% accuracy on the word analogy, so that's looking really good. The big problem with this revelation was, of course, that many other papers later point out that you should not be comparing quality of different machine learning techniques when you are training them on different data sets, and especially as the SIBO and skip-ground architectures were available in the open source toolkit, the Stanford NLP guys could have easily trained Word2Vec on the same data they did train GloVe on, and the comparisons probably look somewhat differently. So that's actually what we try to do frequently. It's also interesting to notice that even before GloVe was published, there was this script that people could have used to get around 78% accuracy. It's actually quite a bit better than GloVe, and it was very reproducible. And then there were like these other guys like Omar Levy and others who did show that actually when they train the GloVe and Word2Vec on the same data set, then GloVe is actually slower, much more memory complex, and produces vectors with lower quality. So it was kind of annoying for some of us, for example, the people working on FastText, that still many people in the community believe that GloVe is better algorithm. So it actually showed that with FastText, we are really much better on that. The FastText library implements Word2Vec and adds as improvement a possibility to also add character engrams, which means that the word vectors will be able to encode much more easily the word structure. It's very useful, especially for other languages than English, when you have less training data and when the structure of the word is much more complicated than in English. For example, all the Slavic languages can can have much better representations when you train with the character engram engrams as the additional input. Just to show like some numbers. If you train word2vec, SIBO, and FastText with subwords, then you can see that basically on the semantic accuracy over like these data sets coming from Czech, German, and English, you don't really do better. You do about the same or maybe slightly worse on the semantic part. But on the syntactic part, there's like huge improvement on Czech, significant improvement on German, and slight improvement on English. So that's quite interesting that you can still do better on like all these word languages with the subword information. And then there's this comparison Glove that we really do, and we actually plan to publish this new model very soon. I think next week, where we did train like on Wikipedia and news 300-dimensional models, and we did compare to Glove that was trained on comparable data sets and using their public vectors, and actually the difference in quality is huge. Like we basically have less than half of the errors that the Glove is making. So I think the quality of the algorithms is like amazingly huge, and it's funny that a large part of the community did believe that the Glove is really the next thing. It's not. It's FastText, of course. So the FastText library also allows to train the classifiers right away, so you don't need to use it just for learning the pre-trained vectors, but you can run classification right away, and there's comparable accuracy to many deep learning models that we compare against, like LSTMs and CNNs with all kinds of tricks and many hidden layers. The big difference is that FastText can be trained on these small data sets in seconds, where deep learning models need to be trained on the state-of-the-art GPUs, and it takes weeks to train them. And on the large data sets, you can't even train the deep learning techniques at all. Like, I mean, if you would go for like some Facebook scale data sets or Google scale data sets with billions of words, then this would like take way too long. You would have to optimize the deep learning models for like very long time, while the FastText is like very simple and can run in minutes. So as I was saying at the beginning of the talk, often it's good to try the basic techniques first, and if they give you the same accuracy and they just run much faster, there's no real reason to use the complex techniques unless for some academic reasons. And the summary of the talk that was about learning of the distributed word representations. Yeah, no, not every neural network has to be deep to be good. That's probably the main message that I was trying to say. And for good performance, you should be using large models trained on as much data as you can gather. That's pretty much it. You can use open source packages for learning the word representations. You can use Word2vec, you can use FastText. I think these are the best choices at the moment. Well, there was special word representations, but then it gets more interesting from the machine learning point of view once you want to model some sequences of words. For that, we are using recurrent networks, and they are a bit more complicated. And I will try to say something about like how these models work, and also about what are their limitations, and something on the side of what we are planning to do to develop models and the data sets that we could use to learn some models that would actually understand the language. Our roadmap plan for the next 10 years. History of recurrent networks is very long, and starts with already like in the 80s, where many researchers who are now super famous were working on these models. The idea was very simple: to reduce parameters and computation over time. It would look something like this. Again, you can start with a bigram language model, but this time you are adding additional inputs at the input layer that are copies of the outputs of the hidden layer from the previous time step. So that's this ST can be seen as a state of the hidden layer in time t, and ST-1 is the state of the hidden layer in the previous time step. So you create this loop in the model because it can cycle the information through the states of the hidden layer, and it can keep it for some time. So it forms some sort of memory, and the memory is learned. It's a very interesting model from the theoretical point of view. Like, for example, Jeff Ellman was advocating a lot for this model in this very nice paper, Finding Structure in Time, from the 1990. People can still read these old papers. I think they're often very insightful and more interesting than many of the recent papers from my point of view. So after the initial excitement, the recurrent networks actually somewhat vanished from or not almost completely vanished from the mainstream research. There was, I think, as far as I remember, there was just basically one group that was really using the recurrent networks a lot back then, at least like the typical architectures. That was at ITSIA. I think there were like a few more groups that were trying to use them, but there was basically no big success. Even from ITSIA, like they tried to use these recurrent networks for like a number of tasks, for example, in acoustic modeling, but their results were simply not good enough. And then there were people who did claim a lot, like since the early 90s, that RNNs actually cannot really be trained with SGD, and they are having some catastrophic problems with either forgetting the information or having exploding gradients that would completely make the training diverge. So there was Yosha Bengio's paper from 1994. So many people were actually giving up because of that paper on the recurrent networks, because they did see it as a proof that these models cannot be trained. But actually, it turned out to be wrong. Like, these models can be trained with SGD, and all that had to be done to avoid the exploding gradient problem was to just clip the gradients, which I did in 2010, and then it was like very easy to use recurrent networks for like a number of tasks, like language modeling, machine translation, and so on. And I could obtain state-of-the-art results on all of them. So it was quite exciting. I did publish the code back then, and immediately, like many big companies, started using the code. I remember in 2011 already there was like MSR and Google and IBM back then using it, and later even other companies did start. And I think that nowadays, like all these big internet companies are using recurrent networks, often actually the LSTM variants, which did sort of replace the original recurrent nets because they are like incrementally better in some cases. In most of the cases, just some historical perspective how people were evaluating language models a few years ago. Nowadays, it's only like a completely different scale. But back then, I was able to like observe these improvements on the Wall Street Journal setup, which is like a famous benchmark from the speech recognition community. Like the difference was like pretty huge, like more than 20% reduction on the word error rate, which is the metric that we are trying to minimize in the speech equalizers, compared to the best 5-gram model. So that was quite interesting. Another reason why people got excited about these models was that actually it showed that with more training data, the difference between the neural networks and the n-grams is increasing. So you can actually be doing better and better as you are increasing the size of the data set. So I think people nowadays do not find it surprising, but in 2010, like it was completely the other way around. People were very skeptical about language modeling ever being able to be the n-grams, and people were kind of giving up the hope, and it's completely turned around, and nowadays I think almost nobody is using n-grams anymore in the research, which is also a pity, because I think these models are also pretty good baselines and can be sufficient in many cases. This other result that was that it convinced a lot of people in the speech recognition and language modeling community back then, that was to show that on the best setup from IBM for broadcast news speech recognition, one can still get significant improvements, because the Wall Street Journal setup is sort of like toyish benchmark, but this IBM setup was really like well tuned for 10 years, and and then still we could get like 11% word rate reduction. So that was pretty big back then. Nowadays, it's very easy to work with these models because they are part of this machine learning toolkit. So people don't actually need to really implement them from scratch, but they can just call some function in a toolkit and it just works. And thanks to GPUs, it's also like much easier to train these models quickly on much more data than what was possible before. Nowadays, I would say that there's wide application, like for speech recognition. People are using these recurrent networks a lot for both acoustic and language modeling. In the machine translation community, like there's this neural machine translation where people are using just purely neural net-based systems. There's also like tons of NLP applications that are using recurrent networks and so on. The downside is that I think people are just using recurrent networks now as a solution to everything, while they are maybe too powerful, or not maybe. For many tasks, they are actually too powerful. If you want, for example, to do, as I was mentioning, text classification, then for problems of this type, it doesn't really seem to be helping us that much to use models that understand sequences or can model well sequences. It seems that if we have just back of n-grams representations in FastText, we can actually do as well as the RNNs on some of these tasks. So I would definitely say that people should always consider the simple solutions first before they go for RNNs, but then RNNs are also becoming pretty simple nowadays because people can just use the existing implementations. Now, of course, from the research point of view, it's interesting to think of like what can we do better than the recurrent networks when it comes to modeling text. With the word representations, like with word2vec, that's really like a very simple statistical model that just ignores the word order and just models the word co-occurrences. The recurrent networks already can model the sequences of words. So what is the next step? Like what can we do to achieve some sort of language understanding in the computers? Actually, it may be surprising to some people, but it's very easy to come up with simple patterns that actually can do normally occur in language, and that cannot be efficiently learned by recurrent networks. Maybe they can be memorized, but not really learned. So an example can be to memorize a variable length sequence of symbols. Let's say that somebody tells you a new word and you want to remember it, and you would want a recurrent network to learn, for example, from communication with you to remember a new word that you tell it. It's actually not that easy. Actually, almost impossible for most of these models that are being used nowadays. So to study these limits of the typical recurrent networks, we did come up with these patterns that contain these simple regularities. We did try to minimize the complexity of these patterns as much as we can, basically in the same style as Minsky was showing the limitations of perceptrons. And we were, of course, not the first ones to study the limits of recurrent networks this way. There are also these papers from the early 90s where people were running similar experiments. But I think that we did actually go a few steps forward in our work, as I will be showing. So our version of learning these algorithmic patterns is to have some model that actually has some sort of like memory. You can see this as a recurrent network that operates on some type of memory that is a topology. We did try at first stacks that have the ability to grow in size. It's actually enough to have 2 stacks in the model to be Turing complete. That is necessary to be able to learn in general, like any sort of algorithm in a finite length. And the model just learns how to operate with this memory. Sometimes people call it external memory, but it's questionable. You can still see it as part of the model, but it's not a memory of the hidden layer. It's sort of like different memory because it has this topology that the first component is different than the than the further components, and it has this growing capability, so you can actually be squeezing more and more information into the stack, and it doesn't have any finite capacity, at least the theoretical model, not our implementation, that actually had some limitations. The actions that the hidden layer actually decides to do on the stacks are like the most basic actions for the stacks, like it can be pushing some value on top of the stack, or it can be popping the value out of the stack, and the topmost value is always visible to the recurrent network. But actually the controller can be feed-forward network, it doesn't have to be recurrent. And the types of memories can be also like different. It doesn't have to be stacks, it can be lists or queues, like anything that has a topology can be used here. Other people actually did work on these type of problems using even memories that do not have the topology, but memory structures that are addressing the information, for example, using the keys to recall values. So that's another type of like associative memory that has been used. So in our case, we did these kind of like classical examples that, as I said, were used already in the papers in the 90s, like to be able to just count like variable number of symbols in sequences where you see different lengths of these sequences in the training data and test data. So you can't just memorize all these combinations, but you have to actually understand the algorithm, understand the regularity, and start generalizing if you want to solve these tasks as well. And there's no supervision for the model. We don't really say where the task ends or starts. Everything is learned through just prediction, so that the network just tries to guess what is the next symbol as well as it can. And for that, it actually has to learn to count. Not surprisingly, the normal recurrent network actually doesn't really seem to be able to learn solutions for these tasks that would generalize to like different distributions that were seen in the training data. LSTM can generalize because it actually can count. It's somewhat hard-coded architecture for counting. That's also something that is not well known, but if you would read the old LSTM paper where the model was introduced, actually there was like the strong motivation for LSTM to develop a model that can learn context-free grammars like these. And then with the stack RNNs, we can learn as well. So it's actually, these models can generalize. And of course, we didn't want to just end up with what LSTM can do, but to show that we can actually learn even much more. And for that, we have these memorization tasks where we have to memorize a sequence of symbols that has variable length. So you actually see longer sequences in the test than what you did see during the training. And we can do somewhat well on these tasks. Of course, it's not a perfect solution, but definitely much better than LSTM that actually doesn't generalize as well as the RNN. But these stack RNNs or list RNNs actually do generalize. Although it's a bit tricky. The most fun example that we were able to produce models, which is where we did show the network a number of examples of binary additions, and then we did train it with SGD again, and then we did analyze what is the output. So this is the visualization of what the network is actually doing with the 10 stacks that it was able to control after it was trained. And it was found that it basically can store the numbers or basically information from the numbers. It can be coding the numbers in whatever encoding it learns itself. And then it's popping up the values from the stacks once it's producing the output, which is basically the predictable symbol. So it's kind of funny. Of course, like there are like the good sides and the bad sides of this model. The good ones are that the theoretical, like from the theoretical point of view, the model is Turing complete as long as it has at least 2 stacks, so it can actually learn infinite length to represent any algorithm, which is what we were aiming for. It has like some simple type of long-term memory because it can grow the memory and it does not really forget the information there. And it can learn some patterns that the LSTMs and RNNs wouldn't learn. Like if you want to, for example, remember a name of a person, then this model in theory could do it because it can just put this name on the stack that has variable capacity. And we did also publish the code. Of course, the bad sides are that if you would want to really represent the memory as a state of a stack, then if you think of it, if you want to store n names of people on the stack and you want to access them later, you would actually have to cycle through the whole stack, which would take n computational steps. So the time complexity of the stack RN would be increasing with the amount of memory that it does store on the stack, which does not seem to be good, because basically the model would get more and more complicated the more information it knows. It's pretty much the same story as why normal computers are not Turing machines. They are Turing complete, but they are not Turing machines, because the Turing machine is more like an interesting theoretical model, but it's not very practical. So we believe that better types of long-term memory are needed in the future, and there are actually have been several papers written on this topic after we did publish the stack RNNs that are advocating for different types of memory structures, but it doesn't seem to be a solved problem, and still I think that we have a lot of things to discover before we obtain a model that actually works well when it comes to the long-term memory. So as I said, like some people, they try to follow up on our paper by proposing, for example, reinforcement learning for these stack RNNs to learn binary multiplication, which I think is already getting too far, maybe a bit on the algorithmic side. That was done by the guys who are now in OpenAI. And one can argue that developing more and more complicated architectures of these memory models and together with the tasks that they are trying to solve is misleading, because then you are basically tweaking both the problem and the model until you obtain some funny result like binary addition, but it doesn't really have all that much practical value. So, so for the last part of my talk, I will say like how we wanted to solve this. We wanted actually to have very interesting and important tasks that we want to solve in the future without being influenced by the model that we are proposing at the same time. So we wanted to basically propose a plan how we can develop these intelligent communication agents without thinking at all about deep learning or whatever stack RNNs, but just thinking about like how we should progress and how we should structure the problems and the tasks that we are working on, so that we have a hope of developing the real strong AI. And that was described in this paper, Roadmap Towards Machine Intelligence from 2015 with Armand Julien and Mark Baroni. And we did decide to focus on a concept of useful general AI. So instead of thinking of like say building some agents that play some Atari games or whatever, we wanted to have AI that will be actually useful for us as humans right away, and that should be our goal that we should be optimizing for. And that's the that we try to define it a bit more precisely. If you want to have useful AI, then we think that it's completely necessary that this AI would be able to acquire tasks from us so that it actually can do something useful for us. And for that, it needs to be able to communicate with us. It needs to understand our instructions in some natural way that would be very accessible to like everyone, and not just the researchers, but to the wide population. And it needs to be able to learn and improve from the mistakes that it does, so that next time it's better. But this learning should happen also like through the communication, the same way as you can be teaching as a teacher a student to perform some task better. You can do it with a human. You can't do it with the recurrent network. So this is something that we are aiming for, like these general points, like learning through communication. And yeah, then there's the small analysis like that. We really believe that these abilities are like necessary, that if we would remove any of them, then we would not really end up with the useful AI. So for the additional components that we were considering and are still considering, it's actually possible to extend this kind of like communication-based learning with some grounding, so that we would actually have more like a natural way of representing the AI in some virtual world, because of there's actually a lot of reasons why we would want to do it. Also, like people are thinking of adding multimodal perception and communication between AIs, but all these ideas are like great to have in the concept, but we do not really need to start with them. So just for the beginning, we can just consider just the communication between a human teacher and the AI that's trying to learn from the communication, and that's already complicated enough. So to give an example, what we would want to develop in the distant future is a system that, for example, can do this. Like you can tell to the machine like that it should check the weather every day before I go to work, so that if it's raining, that it should remind me to bring umbrella. And the machine doesn't really, for example, know how to do this in the first place. And I should be able to teach the machine this ability to perform this task in some natural way, for example, by saying to it that it can find the information about the weather by using the search engine. And then the machine should be able to remember this piece of information and be able to perform the functionality, say, every day in the morning when it knows that I'm going to work. So, for example, not on Saturday and not on Sunday, and so on. So it seems to be a simple task, but if you think of it, what all information the machine would have to be able to process correctly, then it's completely out of scope of, say, just having some recurrent network trained on a lot of these dialogues. It just wouldn't work at all, like no chance. So existing machine learning techniques do not seem to be sufficient for achieving this goal on their own, because we want to be able to deal with unsupervised learning or slightly reward-based learning, where you have like a small number of rewards only available, and maybe just as part of the linguistic channel that even the machine needs to be able to associate with its own internal rewards. And then even like concepts like learning in a compositional and incremental way, that you can build on top of concepts that you learned before, so that you don't have to learn to perform new tasks from scratch. That sounds very simple and intuitive for us as humans, but we can demonstrate that this is exactly what typical machine learning techniques like deep learning doesn't do. Like if you teach a deep learning technique task A and then you retrain it on task B, it will meanwhile forget task A. And also there are some hacks that are trying to go around this. There's no good solution for even this simple not forgetting problem so far, and that all points to this missing long-term memory capacity of these models. So that's really like the problems that we would like to solve. We don't really have a solution for. We just developed a data set which is this simple simulated environment. It's called communication-based AI, and the environment is open sourced at GitHub, so people can be using it easily. It's published together with several data sets of this communication style learning, where it's like very simple, like just being able to repeat, for example, some sequence of symbols. You can treat as a name, but you can just simplify it to two symbols in the beginning to really have the lowest complexity. And so basically the whole environment consists of these tasks that are building on top of each other, so they are actually sharing the language between them. So that's supposed to address both the long-term memory and the compositionality problems at the same time. And of course, you are learning just like with some very weak rewards coming, and that's all. It seems to be doable. Definitely people can learn from these type of environments, and we actually do, like in the real life. But for the machine learning algorithms that were developed while relying on heavy supervision at every prediction step, this is completely out of the scope of what is doable. So it's interesting research problem. Like these are examples that show, like you can have task that when teacher wants the learner to repeat twice something that after it already knows how to repeat something once, then repeating it twice should be just being able to understand the word twice. and it should do it. I don't know, like in say 10 or 20 combinations, like human would probably guess it correctly, but currently doesn't. So there are like these advanced examples that in the slides. I can maybe skip because I think it's obvious that we are dealing with problems that are kind of like out of the scope of what we would want to achieve. You can just imagine that you have the problems that I was just showing. I've written to you in Japanese. If you don't speak Japanese, then it would be very hard for you to actually figure out what is the solution, what you are getting rewards for. But after a bunch of these examples, if you can solve them well, and the new task comes, even if it's written in Japanese, you would already kind of understand that you are supposed to like produce this type of sequence of symbols in this context in like 10 or 20 trials. So it seems to be doable for us as humans to learn this way, and maybe this is the way for the real AI to solve it. So there's also like other groups that meanwhile after we did publish this environment started using it. It's interesting that, for example, the Good AI company that used the Com AI as the basis of their general AI challenge around #1. So they have this website. I think you can still participate. I think it runs till August. And it's basically about the problems that I was just mentioning, how to learn in a compositional way when the problems are simple but are related to each other, so that the new problems are building on top of the previously solved problems. How to build some machine learning techniques that can learn in a compositional way. That's basically the big question for all of us now. And if you have some ideas, you can participate in the competition and see how well you do compared to the others. I think it's very interesting. And of course, the objective function is not to be able just to like solve these tasks, but solve them quickly, so that the objective function is really like about being able to learn quickly. Not just be able to solve these simple tasks, but from small number of training examples, visualization, we don't aim for generalization. If you would not restrict the number of training examples that you can see, then you can just create like as many training examples as you can by just combining all possible combinations of like these variations that that these tasks have up to some length, and just memorize them, but it just wouldn't scale to anything. Yeah. So the test is really performed on different data that you don't really see during the training. To summarize open research problems, we believe that unsupervised learning, where you just have very weak supervision through coming from some sparse rewards or no real supervised signal, just you have to understand which parts of the input correspond to some rewards. That's like a big problem. For example, if somebody tells you a good job, then you should be able to interpret it as a good reward signal, although your brain doesn't really get any hard-coded see a reward signal for like hearing these words. So you have to learn it during your lifetime. So learning how to learn basically is the open research problem. Learning how to use past rewards to optimize the learning at the current moment. That should be like one of the main points that you should be addressing in the future. And then, of course, the compositional incremental learning that I was talking about in the last few minutes is like a big challenge. How to not forget what the learner did learn, but use it actually to learn faster in the future, to generalize faster from less training examples. How do we do that? Well, nobody really knows so far. And memory, actually, all these problems like compositionality and so on would require long-term memory, because if you don't have it, then how can you hope to not forget previous solutions? So it sounds very simple, but again, nobody in the machine learning community has a good solution for this yet. For the conclusion, if you want to develop some strong AI, for example, like intelligent chatbots and so on, I think it's good to be more goal-oriented and really define the problem well and define well the objective metric that we are optimizing. And for that, as I said, we have this communication AI environment, and Good AI company has their general AI challenge. So I think that's good resources to look at. And the communication seems to be necessary for useful, strong AI that are really useful for people, because it's hard to imagine AI that would not have the ability to communicate efficiently with us. Like if you build AI to play, say, StarCraft, then if it plays the StarCraft very well, what do you do with it next? It doesn't seem to be the end goal. It seems to be maybe interesting benchmark for testing the reinforcement learning algorithms, but on its own, it seems to be less interesting than having an AI that you can actually start teaching right away just by talking with it. And to achieve progress, I think it's really important to have standard data sets where more researchers will be comparing their various approaches that they are taking for the research. So I hope this will happen in the future. We did only make our steps, but it will be good if there will be more people interested from the research community in defining well the objective functions, metrics, and the data sets that we want to work on if we are to build AI. So for the final conclusion, I start like with very simple ideas, how to learn some basic features, how to combine these features in some sequential models, and all these things that produce state-of-the-art results in the last 5 or 10 years. There's tons of interesting applications. If we want to achieve something more, I think we will need to do more research, and that's actually the fun part. I did show a lot of problems that people can focus on, and that I believe would lead to the next breakthroughs, like how to solve composition in long-term memory. So I think it's actually a very interesting time to work on machine learning these days. Okay, it was at the end of my talk. So thank you for the attention. And are there questions?
Thank you for your talk, Tomas. I would like to ask you the first question. I think that maybe you will have a lot from our audience, because everybody use Word2Vec, FastText, and stuff like that. But I want to start to ask a question about the last part of your presentation. At the moment, I'm thinking about our next school and what should be the topic for it. And as it is, there is information on the general AI challenge that it is starting first round at the beginning of February, and we actually usually have school at the beginning of the February. What do you think about the idea? Can we like have our school as a kickoff event for starting the first round of this general AI challenge, and maybe to map? It will be more interesting if we will be able to map these simple algorithmic tasks to maybe some parts of the NLP tasks. For example, remember and find some like named entities in text and then repeat them, or something like this. So it's like a equivalent of repeating, but on the other side, it can be used in some systems in natural language processing. So my idea to ask your opinion about possibility for such, on one hand, what do you think about idea to combine our DeepHack and general AI challenges? And on the other hand, can we like map some of the first challenges which will be set for the general AI challenge to the NLP tasks, some primitive NLP tasks?
So I think that when it comes to the hackathon event, I think it's interesting to try to explore some techniques that already kind of work and are, for example, very recent, because then people have very limited time. When I was talking, for example, about the compositionality and the general AI challenge and being able to form a long-term memory, I think that's are like the big open research problems for the next 5-10 years for the machine learning researchers. And I don't think that people can actually solve these in, like, say, a week or two during a hackathon.
No.
So,
You know, I mean that we can start solving them, like that we have these the first problems of repeating. So just try to propose solutions, not to solve them, but it's like a starting point, trying to do something or to discuss the ideas how to do this.
Definitely, like that would be doable. Also, like you can possibly synchronize or communicate with the people who are organizing the General AI Challenge, which is the Good AI company, and ask them, for example, if because they are planning to have like multiple of these rounds. There, as I said, there was the round number 1 that was aiming on the compositionality, which was very like much aligned with what we are doing here at Facebook. So we did actually help them with the challenge. For the round number 2, I think they are aiming for AI safety, if I remember correctly. And I think they plan to have each round going for like 6 months. So next February, they will be probably starting round number 3. So if you communicate with them, then maybe you can just choose some task, for example, like the one that you mentioned, that like combining, say, the compositionality together with some NLP tasks where we are supposed to repeat some named entities in a text, which on the other hand, if you really care just about that application, you can kind of hack some model together that doesn't really need to be able to remember these names, but that can just tell you in which place in text the name was, and in that case you kind of go around the problems. You don't really need to like have a model that can remember like these new types of tokens.
Okay, thank you. So questions?
So thanks for your interesting talk. You mentioned about the objective functions can handle the learning efficiency or the learning speed. So could you give us a few examples of such cases?
Yes. Well, in typically, if we have objective functions that are, say, in a language modeling, where we are trying to build a model that is trying to assign the highest possible probability for the next token in a sequence, like next word, that such function doesn't seem to be good, in a sense that you may end up with a conclusion that all that you need to do is to maximize the size of the training data to be able to predict the next symbol more precisely. And that's actually what many people in the language community were aiming for. What I was advocating for was different, and of course it's not just me, but there are more people who believe that for the AI, the learning speed is actually what we should be optimizing for. So you can see that the training set and test set can be seen as a single set. So you actually do not see this distinction between training set that people can inflate to arbitrary sizes. For example, if you play the Atari games with reinforcement learning, consider that you would try to optimize for having as good performance as possible after 1 million steps, simulation steps at most. So you can produce just 1 million outputs. You can consume just 1 million inputs, and you don't have any pre-training phase. So you really just want to do as well as possible after this fixed number of steps. And that's actually much more like closer to this learning speed than if you have a separate training phase and test phase, where maybe you can just use exactly the same algorithm as 5 years ago to obtain improvement on the test phase just by training on 10 times more data because you have more GPUs or something of that sort. So that creates this fake impression of achieving improvements, while actually the algorithm stays exactly the same, including all its mistakes.
Okay, thank you.
Other questions?
Tomas, thank you for your talk and pleasure having you with us. Maybe a bit of a weird question. You've mentioned our stack RNNs, or neural Turing machines, and the tasks of learning some, what to say, like algorithmic sequences, arithmetic operations. The question, do you have any hopes, or maybe do you see any applications for NLP tasks for the neural networks of this like weird type?
Well, these tasks were more like developed in like using the same motivation as what I was saying about Minsky's parity problem, for example, or the XOR problem, to basically show the limitations of the models when it comes to their learning capabilities. I think that some future versions of these models that would have some good structured long-term memory can be actually very useful for the NLP tasks. But if you take just whatever is the state of the art now, say the neural Turing machines or the stack RNNs, then I don't think actually that these models are like very well suited for some existing NLP tasks, because they're like, if you want to remember some new words, then it's actually much easier to hack around the problem by implementing something specific just for this task, instead of like developing some very complicated machine learning technique that would be able to deal with this. To give an example, even like in normal recurrent network language models, for example, you already assume that the input is one of any encoding of the word. So the algorithm for building the dictionary is actually hard-coded by the programmer. If you want to be more general, you can see that you are reading the sequences of characters, and the recurrent network learns the dictionary so that it has the capacity to learn the new words to some with some limits. But that doesn't really work that well, like for a number of reasons. I don't know if you know the literature on these character-based language models, but they are actually quite limited when it comes to like these recurrent network architectures. They are not very precise and they are super slow to train. So I think that to answer shortly your question, I have a hope that in the future we will have better models. But if you take just what is there now, like the stack RNNs, then I wouldn't just try to apply it to NLP tasks that exist today.
Maybe something to do with conversations?
Maybe, yes. There the memory seems to be better, but I can say that from what I have seen, people are actually trying to do something on this side, like to work with the dialog data sets using some sort of memory models. But the conclusions do not seem to be very positive so far. So I think that we still do not really understand well how to develop models that have the long-term memory.
Thank you.
Other questions? Yes.
Thank you, Thomas. The advice about using simpler architectures, from my opinion, is really neat. But I want to ask you about something opposite. Do you have experience with some tremendous, ridiculously big architectures, but still reasonable, which are still perform well, better than shallow architectures or some smaller architectures? Thank you.
Such example in context of NLP, I'm not so sure. I would say that the interesting deep architectures that did actually do very well in the last recent years were like these famous convolution networks trained for image recognition. So they are sort of like deep and complicated and still are giving very good results. So on that side, yes. When it comes to NLP, the most complicated models nowadays are used for text classification and for machine translation. For text classification, we did only kind of like show that it's not really all that complicated if you really optimize your model well. That was done with FastText. We didn't really do it for machine translation, although I think it's also possible that if you would want to like make a good scalable model that would give like close to state-of-the-art performance by being like way simpler and just kind of shallow, then I think it will be doable. I didn't work on it myself. Actually, there are other people from Facebook from different office who did develop a convolution network-based model for machine translation that is quite a bit simpler than the recurrent attention models, and that actually is beating them in the performance. And I think that even the convolution network can be basically, for machine translation, can be simplified further. So I think that from my point of view, I don't think that there's like some amazing deep models that would do some some surprising things on the NLP tasks.
More questions? Yes.
Thank you for the presentation. Using dynamic memory network, we can give article and get ask questions, get answers. I want to know if they are applicable for, can we give them bigger texts like books, and can they learn books and we ask them questions and get answers? Thank you.
Yeah, well, I'm not an expert on the recent papers on the dynamic memory networks. It's something that you could have asked Jason Weston. I think he has other talk at the hackathon. From what I know from other people working on the same tasks, you can actually do as well or even better without actually using the dynamic memory networks, but again, using simpler techniques. So I am myself not very much convinced that that sort of architecture is really all that much useful in the end. And if you want to be able to answer, for example, questions coming from, say, whole books or, say, whole Wikipedia, there are actually datasets like that. I believe that people are working on tasks like Squad, for example, defined at Stanford, where you can answer like Wikipedia style questions like when somebody was born and so on. And it's not just from, actually it's conditional on the article, but you can find the article automatically too as well. I think that other project published recently here by other people at Facebook research group was this Dr. QA, I think, project, if I remember correctly. And that can kind of like answer questions about Wikipedia without having to have the article that contains the answer, which is the case of the Squad dataset. So maybe you can look at the Squad and the Dr. QA project. But then again, like when it comes to the techniques, I think that it's good to like not overcomplicate the things, and maybe you would be just doing fine if you are using some recurrent network or LSTM and without actually having much complexity. My impression.
Would you agree with me if I say that very loosely something like neural network happens in our brain?
Very loosely. I think that there's a lot of like people who wanted to understand better the human intelligence and they're working on the computers as well. For example, there are like these interesting papers from von Neumann from like the 50s, who was actually like one of the pioneers of computer science. And there you would see a lot of arguments why basically even the computers were developed to mimic something that is possibly happening in the brain. So sure, there are some loose connections. When it comes to artificial neural networks, they can really be seen as weighted Boolean expressions, and then that's also like the basis of a computer. So I think yes, definitely there are some similarities, but one should not really overstate it. And saying that the brain is just a recurrent network, as for example Jürgen Schmidt is saying, that's like way too much in my opinion.
So if you agree with this thesis, then in NLP tasks and in robotics, we need to make some kind of search, like, you know, a beam search is very popular in parsing NLP, for example, or simulating world on several steps before for robotics. So we have that search process in our brain, or do you think that we have something different?
Well, you can say that search is a more general optimization technique than SGD, because SGD itself can be seen as greedy search where we are making a small modification to the current system at every time step that would maximize your objective function if you can define the objective function well. In a real life, for a real human or real intelligent being, you can't define what is the best optimal step that you should be doing. So that's why I actually think that more general search techniques can be like better suited for studying the artificial intelligence than just the SGD-based approaches, because they are just too greedy and require the strong gradients, which require you to have the exact targets. And if you would be looking in that direction, then the communities that did work on like more general search approaches to learning are the people working on, say, evolutionary algorithms and genetic programming and so on, which you can actually also like apply to neural networks. So you can have like these more general algorithms for learning neural networks that's called like neuroevolution.
Can I clarify my question? Like, do we have something like simulator in our brain so we can try different solutions, for example, and choose the best that the simulation showed?
Well, you can definitely think of some past experiences that you did have and try to predict what would be the outcome if you would make a different choice. But maybe this thing that you call simulator is actually what we learned during our lifetime. Maybe it's hard-coded. I don't know, like that would be a speculation to say anything about it.
Thank you.
I don't know.
Thank you. Actually, it's the idea of Schmidt-Huber that we have a model which we can use to simulate different stuff in the world.
Yes.
Hi, Tomas. Thank you for your talk. I have this maybe a little bit strange question. What, in your opinion, will be the next step for the word embeddings? Do we need them anymore? And remembering the OpenAI guys with their sentiment neuron, which is this is the future of the word embeddings, or what? What is the future in your opinion?
Well, to be honest, in my opinion, the OpenAI guys have to produce PR messages, and the sentiment neuron is basically a PR message. So it's not so much on like the research value side, but more like about like having something that you can get into newspapers. After all, like it's a project of Elon Musk, and who is known for like being a guy who needs the attention. So for that part. Else for the future of the word representations, well, of course, like it's very likely that people can still do better. Like, for example, recently, as we did publish the FastText project, we decided to also like produce a new set of these English vectors, and we did find that we can actually do way better than whatever was the state of the art before. That was what I was mentioning in the slides that we will publish soon. And actually, the models are probably online on the FastText website that we will make public next week. So we can still do incrementally better, but it's more like building a bigger database of like words and how they are related to each other. It's definitely not artificial intelligence on its own. Like it's more like a huge statistical model that can be useful, but there's no intelligence in it. It's really just like a large collection of English text that is processed in some good way, and that can tell you which words are similar to each other in which ways. If you are asking about if they are going to be used in the future, then yes, we are convinced that they will be, because I think there will be more and more engineers who will be trying to build applications very quickly that will be based on some input that contains natural text from the users. Say you are building some application for that will be running on the web, and you want to be able to deal with the user input, and you don't have I don't know, like thousands of hours to gather thousands of examples from different users and annotate them and so on. You just want to do it quickly and you have small number of examples. And for that, all kinds of like pre-trained models are gonna help you a lot. And I expect there will be more and more these applications. So yes, I think it will be useful, more like on the applied side, not so much on like the bright frontiers of AI. So I think that the word vectors are not really AI. It's more like just like statistical machine learning.
I see. Thank you.
So no more questions. So thank you, Tomas. And let's thank Tomas for his lecture.
Thanks. Bye.
So see you next time. Have a talk
Okay,
on our
see you.
hackathon. А вы подождите, сейчас я вам еще разъяснение сделаю.